Good morning, dear students. My name is Ferhan Mazher, and today is 20th October 2021, and the day is Wednesday. And right now, I am with the 11th Cambridge class, and the subject we are studying is Physics 5054. Today, we have set our hearts to solve an ATP paper. We call it Alternative to Practical, or we call it Paper 4. And today we have selected May-June 2024 paper. This paper belongs from the Zone 2. The time allowed for this paper is 1 hour. So let's start this paper. So the question number 1 coming up on your screen. Let me reduce the size so you can see the whole thing. And here we have. A student investigates the refraction of light by a glass block. She places the glass block on a sheet of paper and draws around the outline of the block. She uses a ray box to shine an incident ray onto the side AB as shown in the figure 1.1. The ray is incident at point E. Part A is, he says, on figure 1.1, draw the normal at the point E. Okay, so here we have a ray box. This is a glass slab, and the ray box is like a torch, this light or a laser. This is the light which is incident on this face of the glass block, and through it will pass through the glass block, it will be refracted, and then it will emerge from the face CD. So now the first task given to us is you have to draw a normal here at the point E. Normal is a line which will be right angle to this face AB. So what you can do, you can put a set square, you can put a protector here, and the crosshair should be on the E, both the zeros should be on this AB line, and just put a dot of 90 here and then draw this normal. Let me show you. I have drawn this normal. Okay, so here we go. So we are talking about May, June 2020, Physics 5441 paper. So this is, you can see that here I have drawn that normal, and you can see that. In the second part, he says, measure and record the angle of incidence I. Okay, so this is how you will place. So this was the that incident ray, and this is the normal. And you need to put your protector like this. The crosshair are on the E. The zero has been coincided with this incident, the normal, and the incident ray is here. So check how much is this angle. This angle looks like 40 degree. So 10, 20, 30, 40. So your angle of incidence is 40 degree. I hope you have understood that how we have measured it. Okay. So the next question is B part. He says the ray is refracted into the block at an angle of refraction of 25 degree. On the figure 1.1, draw the refracted ray, continue the ray until it meets the side CD of the block. Label the point where the refracted ray meets the side CD with the letter F. So this is the B part. So first of all, I have to mark the angle of refraction of 25 degree. So you can see on your screen, it is showing that how you will put your protector. You see the crosshair of the protector is on the point E, the zero is on the normal. And from here, I will count 25 degrees. So 10, 20, so 25. You can see I put a dot here that shows 25 degree. So this angle is the refracted ray is making with the normal inside the glass block. So I put a dot here. Then I will join that line. So you can see I have joined the E point with that the mark where the mark of 25 degrees. I joined it till it cuts the line CD, the face CD, and I will name that point as F. So this angle is 25 and this angle is 40. This is how you do question number 1. It's B part. The C part is, he says, describe how the student accurately traces the path of the light emerging from the block through side CD. So what you will do, the light ray which will be emerging from the side, the face CD, um, on that light, on the ray of light on the paper, on that light ray, you will put pins. You will put 2 pins. And those pins should be 5 centimeters apart. With the help of a pencil, you will mark their location on the paper, and then you will remove those pins, and with the help of a scale and a pencil, you will join the marks of those pins with each other and with the face CD. So where they will join the face CD, that will be the point F. So you can see my written answer is: put 2 pins 5 centimeters apart on emergent tray. Put circles around pins with pencil. Remove the pins and join both marks with a straight line with the CD. So it's a 2-mark question, and by this question, by this part, we have reached the end of this question. This was the question number 1. So let me show you the whole question. So this was the question number 1. It was of 5 marks, and we are done with this part. So these were its parts, and we are done with it. So let's have a look at the marking scheme, and you can see that here we have the marking scheme. The question number 1 is marking scheme is showing up on your screen. What you can do is pause the video and take your time with this marking scheme. You can check your answers, my answers. I sometimes make mistakes, so please always, you work, I work, your teacher work, always check it with the marking scheme. So pause the video and have time with the marking scheme. Okay, so let's move to the next question. The next question is question number 2, and here we have question number 2. So basically in this question, what they are doing is a student investigates the terminal velocities v of a small steel sphere of different diameters d falling through oil. So a steel sphere falling through oil reaches terminal velocity when the weight of the sphere is balanced by the drag force of the oil acting upon the sphere. The student measures the diameter d of a steel sphere. The diameter of the sphere is 7.82 millimeter. He fills a large glass cylinder with oil. He places 2 rubber bands around the cylinder, one above the other at a distance of 10 centimeters apart, as shown in the figure 2.1. So you can see that here we have a cylinder, and they have put 2 rubber bands outside the cylinder, and the distance between them is 10 centimeters. And this is the first rubber band, this is the second rubber band, and this cylinder is filled with oil. And what they will do, they will take steel spheres and they will drop those steel spheres gently into that oil, and that the steel sphere will sink into this oil. So when this that sphere will pass from the rubber band 1, what I will do, I will start my stopwatch, and when it will cross the rubber band number 2, I will stop the stopwatch. So we will note down that how much time the steel ball took to cover this 10 centimeter depth. So this is the basic of this. And another very important thing they're talking about is terminal velocity. The terminal velocity is, you see, when the ball is dropped into the oil, when the ball, due to its weight, moves downward in the oil, the weight is pulling it downward. But when it passes through the oil gives it a little resistance, and we call it the drag of the oil. And due to the drag of the oil, the drag will be acting upward. The drag force will be acting upward, opposite to the weight. So that is resistive force, which is opposing the motion. So when the resistive force and the weight, which is of the steel ball, they are equal to each other, the steel ball will move with the terminal velocity. The steel ball will move with the constant velocity. At that moment, the weight and the drag force, they will be equal to each other. Resultant force will be 0. That's why the steel ball will move with the constant velocity in the oil. So we call that velocity terminal velocity. I hope that you understood what the story is of this question. He drops the steel sphere into the oil, and as it passes the first rubber band, he starts a stopwatch. He stops the stopwatch as the sphere passes the second rubber band. He removes the steel sphere from the oil in the bottom of the cylinder. He repeats this measurement for the same sphere 2 times. He do that experiment with the same sphere 2 times. He obtains the following values of the time t for the sphere to fall a distance of 10 centimeter. So the time noted by the stopwatch is 0.83 seconds, 0.69 seconds, 0.60 seconds. Calculate the t average, the average value of the t. Give your answers to two decimal place. After the point, there should be 2 digits only. Record your answer on the answer line and in the table 2.1 on the page number 4. So here I have to find out the average of these 3 numbers. And that's very easy. You just add them up and you divide the answer with the 3. So you will get the t average. He says, let me show you how I have done this. So let's go step by step. Okay, so here we go. So we're talking about question number 2a part. So on your screen, question number 2a part is showing up. So we have to find out the average time. So I will add up the 3 observations, and the sum will be divided with the 3. So you can do this on the calculator. So 0.83 plus 0.69 plus 0.60 equals to, divided by 3 equals to, so you will get 0.7066, which means 0.71 second. So the average time is 0.71 second, and this is correct to 2 decimal places, means after the decimal there are just 2 digits. So just why the t average is not recorded to more than 2 decimal places, this is we have taken 2 decimal places only because you see, look at your data. The values in your data, they are correct to 2 decimal places. So that's why our answer should also be 2 decimal places, up to 2 decimal places. So measurement in the data are up to 2 decimal places. That's why our answer is also up to 2 decimal places. Okay, so the next question coming up on your screen is, he says, calculate the average velocity v of this sphere as it falls between the rubber bands. Use the equation shown, record your answer on the answer line and in the table 2.1. Okay, so here the velocity formula is already given. You don't have to memorize it. They say the velocity will be 10.0 divided by t average. 10.0 divided by t average value in our previous part was 0.71. So 10.0 divided by 0.71, and that will be 14.08. So which is equals to 14.1 centimeter per second. So that's the B part, and let's move to the next part. The C part, question number is part 1. He says calculate the d square for this sphere. Record your answer to the nearest whole number on the answer line and in the table 2.1. So the d value in the start of the question is given 7.82 millimeters. So I will take square on both the sides. So d square will be equals to 7.82 square. That will be 61. So the d square value is 61 millimeters square. They have asked us to take this to the whole number. That's why I've written 61 only. Then he says, name a measuring instrument suitable for measuring the diameter d of a steel sphere to a precision of 0.01 millimeter. 0.01 millimeter means 1 by 100. 1 by 100 of a millimeter. You know, your vernier caliper measures correctly up to 1 by 10th of a millimeter. And your micrometer measures up to 1 by 100th, means 0.01 of a millimeter. So we will use micrometer here. Then in the D part, he says, suggest why the top rubber band is not placed close to the surface of the oil. We do not put the top rubber band. Let me show you what does it mean. Where is that? Where is the rubber band? I don't have it. Okay, so let me show you that diagram. So I want you to show that why that they're talking about a rubber band. So they are talking about this rubber band. Why this is at a distance from the top of the cylinder? Because we want this sphere. You have to give time. you have to give enough depth to that sphere in the oil, to that sphere, and then you put the rubber band number 1, so that the sphere reaches its terminal velocity. If you put it near the opening of this cylinder, the sphere will not be at its terminal velocity, because sphere takes a little time to reach its terminal velocity, to achieve its terminal velocity. To allow that time, to allow that depth, we have put this rubber band little away from this top of the cylinder. So let me give you the answer. Oh, sorry. Sphere can reach the terminal. That's a very simple sentence. Why we have put that rubber? Why we have not put that rubber band very close to the surface of the oil? Because we want the sphere to reach the terminal velocity. So that was question number 2 and D part. Okay. Now this is that table in which they were asking. He says the student repeats the procedure using steel spheres. That is that table in which you have to put the T average value. They were talking about this table in the whole question. So T average is 0.71 and the V is 14.1 and the D square is 61. So this is that table they were talking about. So then in the question number 2 E part, he says, let me show you. He says, I'm reading that question. He says, the student repeats the procedure using the steel spheres of different diameters. His results are shown in the table 2.1. You can see that table 2.1 is on your screen. Using the data in the table 2.1, plot on figure 2.2 a graph of V on the y-axis. The V should be on the y-axis. The V values are these values. The V should be on the y-axis against the D square. D square values should be on the x-axis. Start both the axes from the origin. Draw the straight line of the best fit. Okay. So here you can see I have here you can see that I have drawn that grid here. So on the x-axis we have D square, its value in that table. You can see that D values are, the minimum value of the D square is 10, the maximum value of the D square is 61, the minimum value of the V is 2.4 and the maximum value of the V is 14.1. So this is x-axis, this is y-axis. So I will plot these points. Okay. So now here you can see that 10, 20, 30, 40, 50, 60, 70, and this is, I have labeled the x-axis. It is here. I'm representing D square. Its units are millimeter square. And on the y-axis, you can see I've written a 2, 4, 6, 8, 10, 12, 14, 16. So here I'm representing the velocity, which is centimeter per second. So, okay. So now you can see I have plotted those points, and you can see the first point is 10, 2.4. And that is this point, 10, 2.4. Then the point is 19, 4.5. The next point is 26, 6.1. The next point is 48, 11. And the next point is 61, 14.1. So I have plotted these points, and then he asked us to draw the line of best fit. So I have tried to draw the line of best fit. So you can see that there are 1 point above this line and 1 point below this line. The rest of the points, I have joined them together. The line of best fit should be such that the number of points which are left above the line and number of points left below the line, they should be equals to each other. So this is how you will draw the line of best fit. So that is question number 2E part. Then he says, okay, describe the relationship between V and D square shown by your graph. Okay, so V and the D square are directly proportional to each other, because you can see this is a straight line graph and its gradient is constant and it's positive, and it is passing through the origin. Almost it is passing. It's not exactly passing through the origin, but it is almost passing through the origin. So we can say that they V and D are directly proportional to each other. So another argument which you can write here, that when you will double the value of the D square, the V value also doubles, approximately also doubles. You can check this, my argument. Okay, the next part is question number 2, G part. He says, human reaction time error occur when using a stopwatch. Okay, so when your brain asks your hand to start the stopwatch, so there is a certain time between it, and that is called the human reaction time. And so due to this, whenever you time something, there is a certain error whenever you time. That is due to the human reaction. So reaction time. So use the table 2.1 on the page 4 to suggest why the average time, T average, for a smaller sphere is more accurate than for a larger sphere. You see, let me show you that graph, or not that graph, from the table. You see, these are smaller spheres. This is smaller sphere, this is smaller sphere, this is smaller sphere. So the smaller sphere takes longer time. So whenever the time which you are measuring is longer, then the effect of the reaction time reduces. If the time which you are measuring is very small, for example, for this larger sphere, the average time is 0.771 second. And you know, the human reaction time is also 0.5 second, maybe. Some people have very short reaction time, some people have longer reaction time, but at average it is like 0.5 seconds for a reaction. So the reaction time as compared to the time which you are measuring is quite large. So it will have lot of effect on it. So when the spheres are smaller, you can see the time they take is larger. So the reaction time as compared to the time to be measured is smaller. So its effect will be also smaller. So let me show you exactly how you write this answer. Okay. Smaller spheres, average time is larger. So larger T average reduces the effect of reactive time error. Reactive time error. Okay. So I think, let me show you reactive. I so use the word reactive. I think it's reaction time error. So let me check. Where is that? Reaction time error. Yes. The word is reaction time error. I use the word reactive time error. That's wrong. This word here. Let me correct it. Reaction, here we have to use the word reaction. I just want to correct this. Okay. So yeah, start. So the word here is reaction time. The word is reaction time. Okay, basically that word is reaction time. That word, yeah. Okay. This word here is reaction time error. Okay. Okay. So hopefully you understand. And let's increase the size. So this is reaction time error. So then he says, suggest one modification to the apparatus that produces more accurate timings. Place rubber bands further apart. If you move them, both the rubber bands are 10 centimeter apart. Rubber band number 1, rubber band number 2, they are 10 centimeter apart. If you move them further apart, so the time required to cross them will be larger. So you will get more accurate answers. H part is the student removes the steel spheres from the oil at the bottom of the cylinder by dripping a magnet attached to a length of a string into the oil. So he ties a magnet with the string and then it drops it into the oil cylinder, and the steel ball will be tied with the magnet, and then they pull the string out and the ball will also come out of the oil. State why this procedure does not work if the spheres are made of copper. So if the spheres are made of copper, you know, the copper is a non-magnetic material. It is not attracted to the magnet. So this cannot be done for if the spheres are made of copper. Copper is a non-magnetic material. It is not attracted to the magnet. So that was question number 2. It was of 15 marks. Here I corrected this one sentence, one word actually. It was, the word is reaction time. Okay. So let's check. Let me show you the question, the whole question, because I have not shown you the question. So this was the whole question. Most of the question was available. I have done this, most of the question. Okay, so this is the whole question. Paper, let me show you the marking scheme. So here on your screen, you can see that we have that. You can see that we have that marking scheme of the question number 2. What you can do is pause the video and take your time and read this marking scheme carefully. It is very important to read the mark. Very, very important. So question number 2, and here is the rest of the part of the question number 2. So I hope that you have read this marking scheme and you have understood question number 2. So let's move to the next question, and the next question coming up on your screen is question number 3. Here we go. A student investigates the effective resistance of different combinations of 3 identical resistors. She sets up circuit number 1 shown in the figure. So you can see that all the 3 identical resistors have been connected in series. He has put a voltmeter across them. So he will tell you how much the voltage drop the 3 of them all together are taking. Here we have an ammeter that will tell you how much current is flowing through them. We have here we will put a power supply, and here we have a switch. This is circuit number 1. She measures and records the current I in the circuit and the potential difference V across the resistor combination. Figure 3.2 shows part of the scale of the voltmeter. So here we have that. Read the voltmeter scale shown in the figure 3.2. Record your answer on the answer line and in the table 3.1 on the page number 8. So let's read this reading. Okay, so let's check what's the reading on the voltmeter. Okay, so let's check. So this is 1.4, this is 1.5, so this will be 1.41, 1.42, 1.43, 1.44, 1.45, 1.46, 1.47, 1.48. So the reading is 1.48 volt. So the reading is 1.48 volt. So the reading is 1. So here you write 1.48 volt. Okay. Very simple question. So we are done with this. Okay. Now we are going to this question. The student uses 2 more combinations of the 3 resistors, and the combinations are shown in the figure 3.3. So here we have the circuit number 2. These 2 are combined, connected in parallel to each other, and then this combination in series is connected with this, with the 3rd resistor. Here these 2 are connected in series with each other, and they as a whole are connected in parallel to this resistor. This is circuit number 3. She replaces the resistor combination shown between X and Y in the circuit 1 with that of circuit 2, and then that of circuit 3 in turn. Each time she records the current I in the circuit and the potential difference V across the resistor combination. Her results are shown in the table 3.1. The resistance R of each. The resistance R of each combination of resistor is given by the formula R is equals to V divided by I. You remember that formula? Resistance is equals to voltage divided by current. Complete the column headings in the table 3.1. So column headings are these. Voltage, that will be measured in the volt. I, that will be measured in ampere. So you put a A here. Resistor, that will be measured in ohms. So you write an ohm sign here. And then it says calculate the resistance R of each combination of resistors. Record the value of R in the table 3.1. So here I will write 1.48 and you divide the voltage with the current and you get the R value. So let me show you my answer. I've done this on a paper, sir. Okay. So this is question number 3A part, and you can see that question number 3A part, the reading on the voltmeter is 1.48 volt. Okay, so this is that table, and you can see that how you will fill the column headings, and the V value in the first circuit is 1.48. Then what you will do, you will take your calculator and you will divide the voltage value with the current value. So 1.48 divided by 0.13, it will give you 11.38 ohm. 1.46 divided by 0.25, it will give you 5.84 ohm. 1.46 divided by 0.58, it will give you 2.52 ohm. Okay, the C part of this question number 3 is, he says theory suggests that for identical resistors, the resistance of the resistor combination in the circuit 1 is double the resistance of the resistor combination in the circuit number 2. State whether your results support this theory within the limit of experimental accuracy. Give a reason for your answer. Okay, so our answer is the circuit number 2 resistors. If you double it, it will be approximately equal to the resistance of the circuit number 1. Let me show you my answer. Yes, if you multiply 2 with the 5.84, which is the resistance of the circuit number 2, and that will be 11.68, and circuit number 1 is the resistance is 11.38. So the double of the resistance of the circuit number 2 is approximately equals to the resistance of the circuit number 1. So this is within the 10% of up and down. So yes, so our answer is yes. Then it says give one precaution that the student takes on so that her readings of current and voltage are as accurate as possible. So whenever you check, so my point of view is, whenever you check the pointer of the meter, of voltmeter, ammeter, your sight should be looking at the pointers perpendicular to the pointer. Your line of sight should be perpendicular to the pointer, so there will be no parallax error. So the view the pointer of the meters at right angle to the scale. So my dear student, that was question number 3, D part. We are done with the question number 3. So let's have a look at the question number 3 first of all. So this was the question number 3. It was a 5-mark question. So now let's look at the marking scheme. So question number 3 marking scheme is showing up on your screen. I have already checked the marking scheme. What you can do, you can pause the video and take your time with this one. It's very, very important to always check your answers with the marking scheme. So pause the video and check it with your answers, with my answers, or your teacher's answers with the marks. This is how we prepare for the Cambridge. We check our answers with the answers the Cambridge provided us. Okay, so let's move to the next question. The next question coming up on your screen is question number 4. A student investigates the rate of cooling of thermometer bulbs under different conditions. The student takes 2 identical temperature thermometers P and Q. He leaves the bulb of thermometer P exposed to the air, but wraps and secures the small piece of cloth around the bulb of the thermometer Q. He places thermometer P into a beaker of hot water. Figure 4.1 shows the reading on the thermometer P at the time t equals to 0. So if you pay attention to this reading, how much is this reading? So we can so can tell how much is this reading: 80, 81, 82, 83, 84, 85, 86. So the temperature is 86 degrees. So this temperature here is 86 degrees. So record here 86 degrees. And here also write 86 degrees. Record on the answer line and in the table 4.1, the temperature shown at the time t equals to 0. So temperature will be 41, sorry, 80. I said 41. It is 86 degrees. Then he says that the student removes the thermometer P from the hot water and starts the stopwatch. He takes the reading of the temperature of the thermometer bulb at 30 seconds interval for 3 minutes. He repeats the experiment using the thermometer Q. So whatever he did, so he dipped the thermometer in hot water and then it let it cool. So the same thing he do with the thermometer Q, and he obtains these results. Okay. State which thermometer cooled more quickly at the start of the investigation. Justify your answer by referring to the readings in the table 4.1 on the page number 9. Okay. So let me show you my answer. So here we go. So this is 86 degrees centigrade. Okay. So for the thermometer P, you see in the first 1 minute, in the 60 seconds, the temperature dropped from 86 to 37, which is 49 degrees centigrade. And for the thermometer Q, the temperature dropped from 89 to 60 in the first 60 seconds, which is a drop of 29 degrees centigrade. So P, the thermometer P cooled more quickly. P shows a drop of 49 degrees centigrade in 60 seconds, while the Q shows a drop of 29 degrees centigrade in 60 seconds. I hope you understand. It's a little technical answer, but I hope that you have understood that how I'm writing this answer. Okay. So now we are at the end of this question and paper. Last question. He says, suggest 2 conditions that must be kept the same to ensure that a fair comparison is made between the rates of cooling of the 2 thermometers. There can be many things. One thing can be that the same initial temperature of the hot water in which you dip the thermometers, both of them, the hot water should have the same temperature. And the room conditions in which you put the room temperature in which you put the thermometers P and Q to cool down, and that the room temperature should be same. There can be many reasons I just mentioned here too. So that's it. And let me show you the marking scheme. Yes, so that's the end of this paper. Let me show you the marking scheme. Okay. So on your screen, my dear students, you can see the question number 4. Its answers are coming up. So you can pause the video for the time you want to have a good look at this marking scheme. You can pause the video. It's very important to check your answer with them and compare them with the marking scheme. This is how we train our students for the Cambridge exam. They always check their answers with the marking scheme. Okay. So, my dear students, we are done with this paper. So, my dear students, we are done with the May-June 2020 Physics 5054 4-1 paper. This was an ATP paper, and that, oh my God, I by mistake wrote here 4-1 while this number is not 4-1. Let me correct it. This number is basically this number. I made a whole video on it, but this paper was actually 4-2. So it's my mistake. This paper was 4-2. This paper belongs from the zone 2. Okay. So I just made a big mistake. The big mistake is I just wrote here 4-2. So my dear students, today we have done May-June 2020 Physics 5054 4-2 paper. And this paper belongs from the zone 2. And I hope that this paper is clear to you now. And if you have this hard copy, you are supposed to write your answers on your own. This video will help you to understand the questions and their answers. If you find this video helpful, don't forget to subscribe to my YouTube channel and to like this video. If you think that this video has helped you and it has helped you to understand the concepts of ATP and it has made your life easier, and by sitting in your home, by watching the YouTube video, you are able to do this paper. So suggest these videos to your friends by posting the link of this video onto your Facebook, onto your Instagram, or other social media, or social media, whatever social media you are using, because that will also be very big help to me and big appreciation for me for this work. Because when you appreciate my work, it's a great energy for me. Special thanks to my students. Today I want to name them. I don't know the names, but I have students which are watching my videos in Bangladesh, in Pakistan, in Bangladesh, in India, in UAE, in Mauritius, in Brunei. So it's a great pleasure to teach you all. And I think that if I'm helpful to you, it's a great honor for me. So thank you very much, everybody. Have a good day, and God bless you all.